Semigroups and their representations, Lecture 17, Simple Modules. Let us start with the definition of a simple module over a semigroup. Throughout this lecture, we fix a field K. Let S be a monoid and E be the unit element in S. Definition: an S module V over our fixed field K is called simple provided that V is non-zero and the only submodules of V are the zero submodule and the whole of V. For example, the trivial S module K is simple. This is because it is one-dimensional, and so the only subspaces of this K are the zero subspace and K itself. In general, any one-dimensional S module is simple. Here's another example. The regular S module K of S is simple if and only if S is a trivial singleton semigroup, so it consists only of the identity E. Indeed, if S has only one element, then the regular S module is one-dimensional and hence simple. If S has more than one element, then we have the subspace V of the regular module K of S, which is spanned by all differences A minus B, where A and B are elements in S. So this subspace obviously has codimension 1, so it's different from S, and since it has codimension 1, it's also different from 0. And it is obviously a submodule. So this means that in this case, the regular module is not simple. Example 4. Let us look at the natural ISN module K to the power n, and let us prove that this module is simple. Recall that K to the power n has a standard basis E1, E2, and so on En, and the action of ISN on this basis is given as follows. If we have an element sigma in ISN, and I is an index, so if I is not in the domain of sigma, then sigma applied to EI is 0. If I is in the domain of sigma, then sigma applied to EI outputs E with the index sigma of I. To prove simplicity of this module, let X be some non-zero element from this module. So it's a linear combination of basis elements E1 and so on in N, with some coefficients lambda 1 and so on lambda n in K. Then, since X is non-zero, some coefficient lambda I must be non-zero. Consider pi I be the element of rank 1 in ISN, which is the identity on the singleton set I. So it sends I to I, and I is the only element in the domain of pi I. Then pi I, when we apply it to X, outputs exactly the element lambda I times EI, and lambda I is non-zero. And if we apply the transposition of I and j to this element lambda I EI, we get lambda I EJ. And therefore, the submodule which is generated by X contains all basis elements in our module, and so it coincides with K to the power n. So this proves that this natural ISN module K to the power n is simple. Note that if we consider K to the power n as a natural module over the symmetric group Sn, then this will not be simple unless n is equal to 1. Next, let us talk about annihilators. Let V be an S module over our field K. We can speak about two types of annihilators for V. First of all, the annihilator in S of V, which consists of all elements A in S, such that A applied to X is equal to 0 for all X in V. And we also have the annihilator of V in the semigroup algebra K of S. It consists of all elements U in our semigroup algebra, such that U applied to X is equal to 0 for all X in V. Note that, by definition, the annihilator in S of V is the intersection of S with the annihilator in K of S of V. For example, if K is a trivial S module, then the annihilator of this trivial module in S is empty. all elements of S act as the identity on the trivial module, so none of them annihilates it. At the same time, the annihilator in K of S of the trivial module is exactly the subspace of K of S generated by all elements A minus B, where A and B are elements in S. Let us note that the annihilator of any module in S is an ideal of S, of course if it's non-empty, while the annihilator of any module in K of S is an ideal of K of S that always contains 0, so that is always non-empty. Now we can talk about apex. Proposition: let V be a simple module over a finite semigroup S, over some field K. Then there is a unique two-sided cell J, which is also denoted by J sub V, in S with the following two properties. First of all, the elements of this two-sided cell do not annihilate V. In other words, J of V belongs to S minus the annihilator in S of V. And the second property, if some element A in S doesn't annihilate S, that is, if A doesn't belong to the annihilator of V in S, then A is greater than or equal to, with respect to the two-sided order, to the J order of our two-sided cell JV. Another way to phrase it is that if we take S and throw away the annihilator of V in S, what is left has a unique J minimal J cell, and that's exactly our cell JV. And this cell JV is called the apex of the module V. For example, the apex of a trivial S module K is the minimum J cell of S. That is the unique minimal two-sided ideal of S. And all this exists because S is a finite semigroup. Let's prove our proposition. Assume that J1 and J2 are two different J cells in S minus the annihilator of V in S. And assume that they both are minimal with respect to the two-sided order. Take J1 and consider the following subspace of V. We take V and multiply on the left with all linear combinations of elements in J1. Of course, this is non-zero because J1 does not annihilate V. The elements of J1, they do not annihilate V. But also, if A is an element in S and B is an element in J1, then either AB belongs to J1 or AB annihilates V by the minimality of J1. Therefore, our subspace is in fact a submodule which is non-zero, and so it must coincide with V, since V is a simple module. And similarly, K of J2 applied to V is also equal to V by exactly the same argument. But then this means that K of J2 times K of J1 times V must be equal to V, which means that the product of J1 and J2 cannot belong to the annihilator in S of V. But this contradicts the fact that J1 and J2 are two different J cells, and they both are J minimal if we throw away the annihilator of V in S from S. And this contradiction completes the proof. Our next observation is that the apex of a simple module is a regular J cell. Proposition: let V be a simple module over a finite semigroup S over some field K. Then the apex JV of V is a regular J cell. Proof: from the proof of the previous proposition, we have that the linearization of JV applied to V is equal to V. But this means that if we do it twice, then JV times JV cannot belong to the annihilator of V in S. Put differently, this means that there are two elements A and B in JV such that their product belongs to JV. But this implies that JV is regular because it's exactly one of the characterizations of regular J classes from our lecture on Green's relations. And this completes the proof. Now we will construct a certain bimodule. So let J be a regular two-sided cell in S, and let E be some fixed idempotent in J. Let L sub E be the left class containing E, and let H sub E be the H class containing E. Then H sub E is in fact a group denoted by G, so this G is the maximal subgroup of S with identity E. The set LE has the natural structure of a left partial S-act. This is given as follows. If we have an element A in S and X in LE, then this X belongs to the domain of A if and only if AX is in LE, and then A applied to X is equal to AX. The set LE has also the natural structure of a right G-act given by right multiplication. So if we have any element of LE and we take any element of G, so we multiply this element of G on the right and we stay in LE. And since the left and the right multiplication commutes, then by linearization, the linearization of LE becomes a bimodule where the left action is given by the whole of S, so K of S acts on the left, and the right action is given by G, so K of G acts on the right. For example, consider the full transformation monoid Tn. It has a minimum J cell, which we denote by J, which consists of all elements of rank 1. So we have the set 1, 2, and so on n, which we usually denote as n underlined. Given an element I in this set, let Pi in Tn be the unique element with codomain I. Then our set J consists of P1, P2, and so on Pn. All these Pi's are idempotents, and also this J is a left cell, which we call L. Take as E our idempotent P1. Then the corresponding maximal subgroup G consists just of E, that's a singleton group, and the left Tn act L is isomorphic to the natural Tn act. So since our group G is trivial, the right action of G on L is trivial, the trivial group acts trivially always. And so using the linearization, we get that the natural Tn module k to the power n gets the structure of the ktn kg bimodule, so the left structure is just the structure of the natural module, and the right kg structure is trivial, because k of g is just k, that's the group algebra of the singleton group. Now we can talk about endomorphisms of our left S module K of LE. So let J be a regular J cell in S and E be an idempotent in J. Let I be the ideal of S, which consists of all elements A in S, which are not greater than or equal to E in the two-sided order. Consider the algebra A, which is given by factoring K of I out of K of S. And let us note that E is an idempotent of A, and it's a non-zero idempotent by definition. By construction, our linearization of L of n is exactly the A module AE. So that's a module over A, which is generated by an idempotent. This means that it's a projective A module. As I annihilates our AE, we also have that the endomorphisms over S of this module are the same as endomorphisms over A of AE, and endomorphism over A of a projective module AE are always given by EAE. That's a subalgebra, the centralized subalgebra of the idempotent in A. By construction, EAE, that's a linearization of the H cell of E, which means that that's exactly the group algebra of our group G. Consequently, S endomorphisms of the left S module K of LE are isomorphic to the group algebra of the group G. Now we will use our bimodule to define some kind of induction. So our next observation is that the right Kg module K of LE is free. Proof. The left cell LE is a disjoint union of H cells. For each of these H cells, so take such an H cell H and fix some element A in H. Then the map which sends an element B in G to the element AB in H is a bijection from G to H. And this means that the linear span of H is a free module over the linear span of G of rank 1 with basis given by our chosen element A. So the right Kg module K of Le is free, and this means that the functor of tensoring with the Ks Kg bimodule KLE, where we tensor with this bimodule we write on the left, and we tensor over K of G, that's a functor from K of G mod to K of S mod, which we denote by F, and this functor is exact. That's because our module, which we have on the left, Kg module, is free. And of course, by construction then, F doesn't annihilate any G module and is faithful. That's because our module on the left is actually free as a right module over our algebra K of G. Next, note that F sends projective modules to projective modules. Proposition: the functor F sends indecomposable projective G modules to indecomposable projective A modules, reflecting the notion of isomorphism, which means isomorphic modules are sent to isomorphic modules and non-isomorphic to non-isomorphic. Proof: the functor F is just tensoring with a bimodule that's an additive functor, and it sends the projective generator of G mod, K of G, to the projective A module K of L, E. Also, the endomorphism algebra of F of K of G and K of G are isomorphic, and the application of F induces such an isomorphism. Hence, by additivity, we have that F takes indecomposable projective G modules and sends it to indecomposable projective K of G modules. So we can just restrict F to indecomposable summands of K of G. And this completes the proof of the proposition. Here is a consequence, corollary. The functor F sends a simple G module to an A module with simple top. Moreover, if V1 and V2 are two non-isomorphic simple G modules, then the tops of F of V1 and F of V2 are not isomorphic. Proof: let V be a simple G module and P an indecomposable projective cover of V in G mod. Then F of P is an indecomposable projective A module and hence has simple top. By exactness, F of V is a quotient of F of P, and we also know that it is non-zero, so hence it must have simple top. And if V prime is a non-isomorphic simple and P prime its indecomposable projective cover, then F of P prime is an indecomposable injective A module which is not isomorphic to F of P, and therefore F of P prime has a non-isomorphic top to the top of F of P. And this completes the proof of the corollary. Now we can formulate our first main theorem. The map, which sends V to the top of F of V, is a bijection between the set of the isomorphism classes of simple G modules and the set of the isomorphism classes of simple S modules with apex J. Proof: from the previous slide, we know that this map is injective, so we only need to prove that it is surjective. So let U be a simple S module with apex J. Then EU is non-zero because E is an element of J, so it doesn't annihilate U because J is the apex. Therefore, homo over G from the regular G module K of G to the restriction of U from A to K of G is non-zero, because that hom as a vector space is exactly equal to the space EU. By adjunction, so if we move this restriction to induction here, we have that this non-zero hom is isomorphic to the hom over A from the module AE to U, and AE is exactly K of L of E. And this means that U appears in the top of some F of P, where P is an indecomposable projective G module. And this completes the proof of the theorem. Now we can formulate the full classification theorem for simple modules over finite monoids. The theorem: let S be a finite monoid and K a field. Let J1, J2, and so on Jk be a complete list of regular J classes in S. For each I and K underlined, we choose an idempotent EI in Ji, and we let Li be the left class of this idempotent EI. And let Fi be the corresponding functor from the previous slides. Then, for each simple S module U, there is a unique I in K underlined, and a unique simple HEI module V, such that U is isomorphic to Fi of V. In other words, we have a bijection between the set of the isomorphism classes of simple S modules and the disjoint union of the sets of the isomorphism classes of simple HEI modules, where we take the union over all I from K underlined. Now let's look at one example. So consider the monoid T2. So this monoid has four elements: the identity E, the transposition of 1 and 2, the projection π1 with codomain 1, and the projection π2 with codomain 2. These four elements form two J classes: the J class J2, which consists of the identity and the transposition of 1 and 2, and the J class J1, which consists of π1 and π2. So the index of J class here is the rank of all elements in this J class. Both J classes are regular, so let's start with the J class J1, and let's fix the idempotent π1 in it. Then the left cell of π1 is the whole J class J1, and the H cell of π1 is a singleton group. The group algebra of this group is just K, and this has the unique simple module, namely K. And the module F1 of K is exactly the linearization of our left class of π1, and this module has dimension 2, and the base is given by π1 and π2. The difference π1 minus π2 spans a submodule of this module, and the quotient of the linearization of Lπ1 over this submodule is a one-dimensional module. In fact, it's a trivial T2 module. So this is our first simple T2 module, and it exists over any K, the trivial module. Now let us move to the J cell J2. So this has a unique idempotent E, the identity, and we have the J2 is equal to the H class of E and is equal to the left class of E. And the group HE is exactly S2, the symmetric group on two elements. Now we need to consider two cases based on the characteristics of K. First, consider the case when the characteristic is not 2. In this case, S2 has two simple modules, both of dimension 1. The first module is a trivial module, it's one-dimensional, and both the identity and the transposition of 1 and 2 act as the identity on this module. And the second module is a sign module, where E acts as the identity and the transposition of 1 and 2 acts as -1. As J2 is the apex of our module, the elements of J1, which are strictly smaller than J2, they must act as 0. So both π1 and π2 must act as 0 on our modules. So we take our simple S2 modules and we postulate that π1 and π2 act as 0, and we get two simple T2 modules. One of them, which is trivial over S2, π1 and π2 act as 0, and the other one, which is sign over S2, π1 and π2 act as 0. And finally, we have to consider the case when the characteristic of K is equal to 2. In this case, the symmetric group S2 has only one simple module, namely the trivial module over this group. In fact, the sign and the trivial module, they coincide because -1 is equal to 1 in characteristic 2. And now we can extend this to a T2 module by setting that both π1 and π2 should act as 0, That's because J2 is the apex, J1 is smaller, it must act as 0. So altogether, in this case, we have two pairwise non-isomorphic simple T2 modules. So if the characteristic is not 2, we have 3. If the characteristic is 2, we have 2. A warning: if we take the trivial S2 module and extend it to a T2 module by setting that both pi1 and pi2 act as 0, we will not get the trivial T2 module. So the trivial T2 module is the one where both pi1 and pi2 act as the identity, not as 0. Okay, some additional problems and questions at the end. Problem question 1. Determine both the annihilator in KFS of KFS and the annihilator in S of KFS. Problem question 2. How does the functor f in the lecture depends on the choice of our idempotent E inside J? Problem question 3. Describe explicitly all simple IS2 modules over any field. Problem question 4. For S, J, E, G, V, and F as in the lecture, determine the endomorphism algebra of F of V. And problem question 5. Describe explicitly all simple T3 modules over any field. Thank you very much and see you next time.